All right, we have started recording and start the backup also. Okay, yes, set now. So as I mentioned, we are going to start with this new chapter, Deflection of Beams. Uh, so in the previous one, we had considered various kinds of applications. We learned something new really in the context of thin wall pressure vessels and thick wall pressure vessels, but ultimately it was just an application of the analysis of stress. Uh, in this chapter also on the deflection of beams, the spirit is more or less the same. There is not much new theory involved. In fact, it is just bending of beams again. However, unlike previously, when our main concern was to uh, look into the various kinds of stresses, particularly the normal stresses due to bending, which was also referred to as the bending stress or the flexural stress. And later on, our concern was shear stresses in beams. Here, we are not going to be bothered with the stresses. Rather, as the name of the chapter suggests, our concern will be with the deflection of beams, meaning that under some kind of loading, and when I say some kind of loading, I mean that in the typical case, we are always going to have transverse loading, that is loading perpendicular to the longitudinal axis of the beam. Under that situation, how much the beam deflects from its longitudinal undeformed position. You have all seen that beams bend. Our concern here will be to find out how much it is bending, rather than looking into the other aspect which we have been talking about, that is the stresses that are being generated. Okay, so this is a very important step when we go into the design of beams, because all this while everything that you have done, that has been from the point of view of the strength of the beams. Strength means if you can analyze a beam for stresses, then you can compare the stresses developed with the ultimate stresses, with the allowable stresses, with the yield stresses, and considering various factors of safety, you can design a beam such that the stresses do not cross a particular threshold. That was the whole point of finding out the stresses in the beams, that the beams should be designed in such a way that the stresses do not cross a particular threshold. However, there is another aspect to the story, which, as you can guess from the chapter's name, is that the beams should also be designed in such a fashion that certain geometrical constraints must also be respected. So, based on what I have been telling you, can you give me an example where such a consideration may be very, very important? That fine, the bridge or the building should not break down. Breakdown means the stresses should not be so high that it breaks apart. But tell me an example where the deflection may also be a design consideration, that it should not have deflection beyond this much or beyond that much. In what kind of practical situation that is very familiar to all of us, do you think such design considerations would be important to a professional engineer? Please try to answer. In what kind of consideration it would be important to see that the deflection of a certain structure is not beyond a certain value, is not higher than a certain value. In what kind of structure?
Wings of airplane.
Sorry?
Wings of airplane.
Wings of aeroplanes. Why do you say that?
So like if there is deflection, it might affect the aerodynamic characteristics of the wing.
Hampered. Okay.
Like the shape of the airfoil, if it deflects, it might destroy the lift and drag.
Right. But there is a small thing which many of us are not aware, is that when the airplane wings are designed, they are designed in such a fashion that they can undergo huge amount of deflection, like the kind of terribly afraid, like during the design process or during the fabrication process, they are subjected to such high kinds of loads in the transverse direction that the wings actually flap like the wings of a bird. That kind of thing never actually happens in practice. When you fly on an aeroplane, you will never see the wings of an aeroplane flapping like that. But during testing, they make the aeroplane wings flap like that. So even if so happens that God forbid such a thing arises, it can still sustain that kind of deflection. Okay. So ideally, we do not want huge amount of deflection in the aeroplane wings, but what I'm trying to say here is that even if it happens, it is not necessarily the end of the world. Okay.
So our daily life example, the exam pad which we use for holding the papers. So if we apply more pressure also, it should not bend and it should not disturb the purpose which it is used for.
What example? I could not hear you that part.
So exam pad, the plank.
Exam pad.
Yes, sir.
You mean the clipboard?
Yeah, yes, sir.
Okay.
The wooden part of it.
Yes. Right. But usually you keep the wooden the clipboard on the table, right? So it has a solid backing beneath it.
So, but sometimes we use it to support the papers on which we are writing on in a free space. So we
Like
need the paper
your
to be
hand,
plain.
like you hold it in your hand, like the doctors use it.
Yeah, exactly. Yes, sir.
Yes.
So if the table is too high, then we will like keep it in a slanted position.
Okay. Anything else? Like we'll be in serious trouble if the deflection is too high. See, you can solve any number of equations. I know you're all good in maths. You can do that. If I teach you after a couple of hours of lectures, you can all do the problems from this chapter. But it is good to at least think for 5-10 minutes about why exactly or what kind of real life thing would you be using the lessons from this chapter. Okay, that is why I'm trying to spend some time discussing this with you.
So pillars while constructing a building.
Let us not discuss about pillars in this chapter. Okay, so we'll come to pillars, the whole story associated with pillars in the next chapter when we talk about buckling. Okay, there also deflections are important, dangerous, whatever, but we'll talk about that later. So because in pillars, the thing is that you are subjecting the pillar to load in the longitudinal direction. That is, it is subjected to axial loads. Okay, I'm talking about the kind of things where the structures are subjected to transverse loads, that is perpendicular to the longitudinal axis.
So the horizontal bars on the bed.
Sir, bed.
Yes,
The
yes.
horizontal bars.
Very good. So if your bed, if the horizontal bars on your bed, so even if it is a wooden bed, you also have horizontal bars. The modern plywood beds don't have those horizontal bars, but I mean some of the older wooden beds they have had that, and the very modern metallic cots they also have those horizontal bars. Now, if those horizontal bars deflect too much, then your entire bed will become curved, and you'll feel like you are sleeping in a not on a bed, rather in a trough kind of thing. Okay, it's going to be very uncomfortable. So that's a good example, a solid good example where we don't
Sir,
want
railway tracks.
Yes.
Railway tracks, if it gets somewhat curved, then accident can happen.
Yes, yes, but okay, but the thing is that the railway tracks, so when you are saying railway tracks get bent, you are saying that they get bent. So suppose you have a straight railway track. Let me draw this thing. Do you mean this? That suppose you have, like we are seeing from the down into the ground, we have this railway track, okay? We have a railway track like this. And do you mean to say that it becomes curved like that? This one?
Yes, sir, something of this sort.
But usually this kind of deflection is again due to the axial loads which are acting on these beams. Okay, that has to do with the buckling of these railway tracks. Because the transverse loads, the huge transverse loads that actually take place on this railway track, if you see from the side, this is a railway track. The loads on this are due to the passing of the railway. I mean the train. Okay, and this is the ground beneath it. So, I mean, it can deflect a little bit here, but not too much. I mean, that is not a severe issue. There is certainly an issue, but that is not a severe issue. Of course, what you said about this kind of a deflection, that is important, but again, that is not due to loads which are acting in this transverse direction. Not in this, you don't have much loads in this direction.
So fracturing of hand. Fracture of hand,
actually, it is not just deflection, okay? So there is a certain threshold limit of the stresses that our bones can take. If it goes beyond that, then it fractures. Okay, so it is not directly a case of deflection. Rather, it's a kind of stress consideration. What about bridges? Because the way that bridges are designed, they can sustain huge amount of stresses. There is no doubt about it. But suppose it so happens that you have a bridge. Okay, you have a bridge like this. And this bridge, you can think of it like a double overhanging, simply supported beam. Okay, suppose the bridge, it deflects like that. Can you imagine the kind of discomfort it will be traveling on this thing? Okay, if over time the bridge becomes like this, or God forbid, if this kind of deflection takes place in a dynamic fashion. Now, all of you may be thinking about the resonance of bridges, which you have probably the Tacoma Narrows Bridge example. How many of you have come across that example, the Tacoma Narrows Bridge example?
Yes, sir.
Yes, sir.
Yeah, you have learned that is frequencies matching with the wind frequency, then resonance happens, right?
Yes, sir.
Yeah, that is not correct. Okay, so the Tacoma Narrows Bridge did not fail due to resonance. That is actually a mistake that is propagated mainly because of the very good textbook otherwise, but that is one mistake there is that in that textbook by Resnick and Halliday, which many of you may have studied during your +2. Okay, the Resnick, Halliday and Walker and various other versions of Resnick and Halliday. So it's actually a mistake there. It is not due to resonance. Okay, so that is basically due to aeroelastic flutter. That's a different phenomenon. Okay, it has some connection to resonance, but it's not resonance. So I can share one article with you later on. You won't understand much of the article, but it's a properly investigated thing. So Tacoma Narrows Bridge, problem was deflection. Okay, and problem was that it broke down also, but it was not due to resonance. So, but the key point that I want to highlight in the context of this chapter is that in bridges, if you have an undue amount of deflection, it is not good. Okay, it is very, very bad. You don't want that. So in the case of a bridge, you certainly want to have the deflections limited to a certain extent only. And when you design a bridge, you also have to note that at different times of the day, at different times of the year, the nature of the loadings on the bridge, because of the movement of the traffic and the varying nature of the traffic, is also going to be different. So a lot of different design considerations and design cases have to be kept in mind for the design of beams. Okay, so it has to be designed for strength, meaning that the stresses should not be too high so that it doesn't break apart. Furthermore, the deflection also should not be too high. Okay, otherwise it is a practically useless beam. I mean, it's still standing, but you can't travel on it. Anything else? What about buildings? The tall skyscrapers that you see. Suppose you have this kind of a very big thing, okay? Very big skyscraper. like the Burj Khalifa. What kind of transverse load it is experiencing, this building?
So due to wind.
Absolutely. Very, very high loads due to wind. Okay. And in fact, I think the fluid mechanics guys and the thermofluid science, you are going to study this in a week or so, if you've not already started it. You are going to study something called the boundary layer theory okay. So there you will see that you can almost model the wind effects on a building using boundary layer theory. Okay, and I'm not going to get into that, but the fact is that on buildings the wind load is extremely high, especially on the tall skyscrapers. This is going to be significant. So there is a high chance that this building is going to deflect like that. Okay. Now one may say that fine, it is deflecting as long as it is not breaking apart, it is fine, right? But understand that people are going to live on it. They're going to work and live on it, on this building. And if the deflection are going to be too high, it is not going to be usable. Okay, so again, we are considering all of this from a very statics point of view, but do understand that wind loading is very dynamic in nature. So these kinds of deflections can also be extremely dynamic in nature. It's not just that there's one building standing and there's one nice deflection like this and it's standing like that. It's not like that. Okay, it's much more complicated because it can move around and sway like that, sway and swing like that. First of all, in the statics case only, the deflection to be too high. Okay, so if the deflection is not too high in the statics case, you can reasonably expect that in the dynamic case, it is not going to be too high. But don't be too confident about it because there are some special things which can happen in the dynamics case also. Okay, so we have some idea of the kind of situations where deflection of beams can play a crucially important role. Okay, it is important to keep this kind of structure which is subjected to transverse load. This is what I wanted to say. Okay, now we come to what we have to do in order to calculate these deflections. Okay, so as I said, there is not much new theory. It is basically just a reinterpretation of already done theory. And what I mean by that is that let me go back to our course website. I hope all of you can see the course website page that I have opened on my screen.
Yes, sir.
Yes.
Oh, yeah. I've opened on my screen. I hope all of you can see this, right? This fact web page. And I'm going to open the, which one was it? I think this was the first one. So I'm opening the class notes 1. Let me see if I have it here. Just give me a second, okay? It's not here, sorry, maybe class notes 2. Yeah, I think it is here. Yeah, this is the one. So all of you can see this class notes 2, bending of beams, bending, deformation and flexure formula that I have opened on my screen.
Yes, sir, we can see.
Yeah, okay. So what I want to show you is this one. Okay. This thing. Okay, this M is equal to EI by rho. We have been using this thing fundamentally in almost everything that we have studied since we introduced deflection, bending of beams, because even though we may not have directly used this formula except for maybe a couple of problems in the tutorial sheet, but this has been at the basis of many of the later formulas that we have derived. Okay, so E is the Young's modulus, I is the second moment of area, M is the bending moment at any particular cut section of the beam, and rho, this rho is the radius of curvature. Okay, so just to remind you, this is the bent form of the beam, and this is the radius of curvature. You'll have a center of curvature of this thing. This is the radius of curvature. So that is what I mean. Let me get back to deflection of beams now. So we are going to start with that formula. Okay, so this m is equal to EI by rho. Now, this rho is the radius of curvature. So this is 1 by rho. What is 1 by rho then? If rho is the radius of curvature, what is the reciprocal of the radius of curvature? Again, from your first year maths, or maybe even earlier. You remember this? Is it not the curvature itself? Am I audible to everyone?
Yes, sir, you are audible.
Yes,
but we
what
didn't
is
get
the
that.
curvature?
But are you not familiar with this thing, the radius of curvature and the curvature formulas, all these things?
The radius of curvature is familiar to us, but curvature is not. Right?
Yes, sir.
I will write one formula because this used to be given a lot of emphasis back when we were first year students here at Kharagpur itself. So I'll just write one formula. You tell me if you have seen this before or not.
Yes, sir, we have seen this.
Yes, sir.
Thank God. Thank God.
Yes, sir. Yes, sir. In JEE.
In JEE also you have seen this. I had not seen it during my JEE preparation. I saw it after coming to IIT Kharagpur. Okay. Anyway, so we have this thing. Okay, maybe I saw it during my JEE preparation, but I don't remember. All right, so we have this thing, right? So if you have any curve, okay, if you have any curve like this, so this is y and this is x, and this has a certain curvature. This curvature is given by this particular formula. It's not a particularly difficult derivation, but we are not going to go into that, okay? Otherwise, I'll never finish this deflection of beams. So we have this thing. Now, as with everything else that we have been discussing, we are going to say that the deflection is going to be there, but it's not going to be a huge amount of deflection, meaning that this particular thing, this dy dx, it is not going to be too much. What I mean by that is that suppose you consider a beam like this, and we are going to consider this particular example in order to fully solve this thing. So we have a cantilever beam, and suppose you consider that the x is like this, the y is like this, and there is a load. This blue colored arrow is the load, okay? A point load or a concentrated force P acting at the tip. As a result of this, this cantilever beam is going to deflect, and you know that it is going to deflect like this. Okay, so this kind of a deflection it is going to undergo. Now, you have a y here, you have a x here. So please try to understand that when we are talking about this d square y dx square or dy dx, we are basically thinking in terms of the deflection of this beam represented in terms of this different values of y that it is undergoing as we move along the x. So at this particular x, there is a certain value of y. At particular x, another x, there is another value of y. So different values of x, there are different values of the y. Together, all those different values of y, together they are representing the deflection of the beam. That is what is meant. And that is nothing but, mathematically speaking, just a representation of a curve. So the deflected shape of the beam can be understood in the form of a deflected curve or some kind of a curved line. Okay, so all these derivatives, they refer to the slopes and the second derivatives of this deflected shape of the beam. Okay, so if you can wrap your head around this simple concept, then everything else is just algebra and calculus. Okay, and what we are going to say importantly is that this slope is not going to be too large, meaning that for the practical scenarios that we are going to be interested in, the magnitude of this dy dx, this is much less than 1. If it is much less than 1, then the square of that is even less than 1, is even more less than 1. meaning that this denominator 1 plus dy dx square, that is practically 1. Okay, so 1 plus dy dx square, that is almost equal to 1. We might as well neglect this. So what we're going to say is that 1 by rho is equal to kappa is almost equal to just the second derivative. And this makes our life a lot easier. So we are going to substitute this expression back here, and let's see what happens then.
Excuse me, sir.
Yes.
So actually at the point where load is there, so dy by dx is much less than 1, or is it significant at that load?
So it is like this. Okay, so good question. That whenever you have these kinds of beam considerations, you are not supposed to look or any of these theories, they are not strictly valid at the location where the load is given. Because if you microscopically zoom into this thing where the load is pressed down on this beam, you will see something like this, that this is the undeformed deflection. But after this thing has been pressed down, it will look like this. This thing will look like this. Okay, so a very complicated kind of deflection takes place at this point. Okay, and the kind of theories that we are doing, which are gross macroscopic theories, they are not going to be able to handle the real scenario which is happening at this tip. So what we say is that as long as you stay slightly away from these loads, then you are safe to use these theories. So we never actually say that we are going to write the deflection strictly at x equal to 0. But of course, for approximate purposes, we write like that, but we have with the understanding that we are actually slightly away from the actual application of the load point. Okay, and this particular principle, where we always stay away from the actual application of the load points, is referred to as the Saint-Venant principle. Okay, so remember this, the Saint-Venant's principle. Okay, so the actual nature of the loads specifically at the point of the loading is going to be significantly different than what is predicted by these kinds of undergraduate level theories.
Yes, sir, I understand. So even when there is a uniform distribution load, then this will happen, or it will not happen?
So uniform distribution of load doesn't have this problem. Okay, it is only in the case of point loads then that you have this problem.
So when there is a uniform distribution load, then dy by dx will be?
Yeah, so yeah, oh, you are asking like what is going to happen then? I'll show you. That is also one of the examples I'm planning to demonstrate. Don't worry. I'm going to take both point loads as well as distributed loads. Okay, we are coming to that. So getting back to this thing, I'll just try, take this the reverse way. So this is EI 1 by rho. 1 by rho is d square y dx square. And this is equal to m. Now what is m? For the particular, so this is just about the kind of theory, the general theory that I wanted to discuss. Finished. Okay. You have this second order differential equation. For different cases of beams, you will have different values of the m along the longitudinal axis. You have to find this out and solve this differential equation. That is the whole point of this chapter. Like mathematically speaking, this is the funda, but the devil is always in the details. So we actually have to take up certain specific examples to understand how do you tackle the different cases. So the rest of the discussion starting from this point will be concentrated on considering the very special cases associated with different kinds of loadings and different kinds of beam supports. Okay, so the first example that we're going to take up is exactly this example itself. Okay, this one only. So we have this cantilever beam. This is X, this is Y, and this is our load. Now, as always, we have to determine this M. And for that, what we are going to do, we are going to take a cut section at a distance X from the left end. So what is going to be the M there? So usual procedure as always, we represent the V like this, the M like this. So this is at the exposed end of this cut section to the left. You also have this P here. So if you do the moment balance, what are you going to get for the M?
Minus px.
M is equal to minus px. That's all there is to it. Okay, so M is equal to minus px. So what we are going to do is we are going to substitute this expression of M equal to minus px back here. Now you see, for this particular example, our Young's modulus is a constant all along the beam. So E is not a function of X. Furthermore, this is a prismatic beam. Prismatic beam means the cross section is not changing along the length of the beam. It has a uniform cross section all along the length of the beam. The implication of that is that the second moment of area that is not changing along the length of the beam. So E is a constant, I is a constant. This E times I, that is sometimes referred to together. So this product EI, sometimes it is referred to as, not sometimes, it is always referred to as the flexural rigidity. Okay, just a name. Okay, don't worry, I mean, about the name, but it's good to, I mean, once you have completed this chapter, it's good to know that this particular combination has this name, flexural rigidity. Furthermore, this P value, that's just a constant, that P itself is not a function of X. So now you see that this particular equation, that is a second order linear differential equation. Okay, that's a second order linear differential equation. And it can be easily solved to find out Y as a function of X. Okay, that's what we are going to do. Now, if you do that, how many constants of integration are you going to end up with?
2, sir.
You're going to end up with two constants of integration. Very good. So, so let's actually do that. Okay, first integration. So integration with respect to X. We have one constant. This C1 is the unknown constant of integration. We do another integration. All right, so we have ended up with these two constants of integration, C1 and C2. Otherwise, this Y as a function of X, we have already found out. Whatever the rest of the work involves, that is just to find out the values of these unknown constants of integration, C1 and C2. You tell me, how do I?
Sir, by boundary condition.
Boundary condition.
Boundary conditions. Very good. So what boundary conditions will you use?
Sir, at x equal to L, y equals 0.
Very good. So we have to use boundary conditions. So at x equal to at x equal to L, at x equal to L means the point where this beam is attached to the wall. Please understand that this entire length, is L. Okay, at x equal to L, we have y equal to 0. That is a guaranteed fact because it is fixed to the wall, it is attached to the wall. There is no chance of any deflection either in the positive y direction or in the negative y direction for this beam. So y is equal to 0. You need another condition. What is that?
So at x equal
Sir,
to
y is maximum at x equal to 0.
Y is equal to maximum at x equal to 0. Okay, there is one condition. Anything else?
dy by dx equal to 0 at x equal to L.
Why do you say that?
So actually approximately we are taking 0 and at the end where it is attached to that fixed point.
Your answer is actually correct. Okay, so this is Niranjan, right? Or who said that answer?
Anirudh.
Anirudh, okay, Anirudh. I'm just guessing from your voice. Okay, so we have this beam. Okay, I'm only drawing a single line here to represent the entire beam, not like a rectangle here. But please understand that this represents the longitudinal axis of the beam. This is the undeformed configuration. And you have the wall here. Now, when you have various kinds of attachments or supports, that those different kinds of attachments or supports leads to different conditions at those boundaries. When it is attached, this is very easy to understand that y is equal to 0, meaning the deflection is 0. But when it is attached, the other name for this is fixed. Sometimes it is also referred to as clamped. So fixed or clamped end. Okay, so these are certain terminologies which you should be familiar with. Fixed or clamped or attached. Okay. So when you have these kinds of things, the deflection always occurs in this kind of a fashion. Sorry, my writing app just closed down arbitrarily. So when it is clamped or fixed, the deflection always takes place like this. This is a, very exaggerated view, but if you zoom into this thing, if you zoom into here, you will see that the undeformed configuration is like this. The deformed configuration is like this. Okay, so in the deformed configuration also, at the point of location of this fixed or clamped end, this remains straight. Okay, this is the hallmark of the fixed or the clamped end. You are not going to have this kind of a situation if instead of this fixed or clamped end, you have a simply supported end, which we are also going to take up next. Okay, so right now for the solution of this problem, the important thing to apply from this knowledge is that at the fixed or clamped end, that is at x equal to L, you are going to have dy dx is equal to 0. Okay, now this is just a case of doing algebra correctly. So you can do it later on. You will find out that after solving this thing, you will find out that at x equal to 0, okay, after a solution, after solving, you will find out that this is PL cube by 3EI and with a minus sign. So the magnitude of the greatest deflection will come out as PL cube by 3EI. This is a very, very important result. Okay, I always encourage my students not to mug up results of various problems like this, but this is such a typical important example of a cantilever beam under tip loading that I am asking you, I'm requesting all of you to please remember this result, that the maximum deflection for a cantilever beam which is subjected to a tip loading means at its tip, that is going to be PL cube by 3EI. Okay, at the same time, you also try to find out what is the value of this dy dx at x equal to 0. Okay, you will get something like PL square by 6EI. Okay, please do this. Not now, you can do it later. I'll go on to the next example. I hope none of you will have any problem in actually solving for this C1 and C2. In case someone has any problem, please do let me know. Okay, you have all done these kinds of things earlier in your maths, maybe even during your +2. So it should not be a problem, but in case someone has some problem, please do let me know. Okay, it's not a big deal. Okay, next example. So here we are going to consider a simply supported beam. Please note that in the earlier example that we have taken, this is a statically determinate case. Okay. The next example that we are now considering, this also is a statically determinate case. Courtesy the utilization of this kind of a roller support here, okay, or a wheel support here. Had this also been like this, then this would have been a statically indeterminate case. Okay. Now, as far as the reaction supports are concerned, how many unknown reaction supports are here? Of course, I should show you the loading that is taking place here. This is a uniformly distributed loading. So tell me how many unknown reaction supports are there? Reaction forces are here.
3 unknown.
3 unknowns are there. Okay. There's going to be one vertical unknown here, one horizontal unknown here, and one vertical unknown here. There is not going to be any horizontal unknown here because the way that this structure has been presented, there is no resistance against the horizontal movement of this end. And since there is no resistance against the horizontal movement of this end, there is no reaction force also here, okay, in the horizontal direction. It is only in the vertical direction that you are going to have some kind of a reaction force. Okay, so the strength of this thing is W, and it is in the unit of Newton per meter. Now you tell me if the entire length of this beam is L, what are the values of the reaction supports? So what I mean to say is that so if I draw the free body diagram, I'll have a R1 here and a R2 here, and of course one R3 also. You tell me what are the values of R1, R2, and R3.
WL by 2.
So R1 is going to be equal to R2 is going to be equal to WL by 2, and R3 is going to be equal to 0. Okay. Now, what we can do is, just like in the previous problem, we can take a cut section like this. If we take a cut section like this, then what is going to happen? We are going to end up with this piece where you are going to have this R1 and you are going to have the distribution that is relevant to that part. And of course, you are going to have the usual internal loads. This is the shear force and this is the M. And from this free body diagram, you can determine the expression for the M. That you can do. And once you can find out the M, and you understand that this distance is X. Okay, from the left, this distance is X. So you can find out M as a function of X. And then whatever you did in the previous case, this EI d square y dx square is equal to minus px. So instead of this minus px, you're going to end up with a different sort of expression and you can proceed. Okay, and in fact, this example is actually solved like this in your textbook. I'm considering only the simple cases, the solved example cases only, because these are very important typical cases. Now, that can be done. Okay, but I don't want to do it. I want to do it in a slightly different way. So what I will do is I will update my theory a little bit. What I will do is I'll go back to this expression, to this equation. EI d square y dx square is equal to m. Now, apparently for no rhyme or reason, I will, instead of integrating this, I will differentiate this. You will see in a moment the motivation behind that. I will differentiate this again with respect to x. Okay, what is the benefit that I have obtained from here by doing this differentiation? You see this
dm by dx
dx
equal to minus 2.
dm dx is actually v, not minus v. Okay, so dm dx is v. Okay, v is the shear force. All right. Now, next I will do another differentiation. So now this has become a fourth order differential equation. What is dv dx?
It would be a constant.
Minus w.
Minus w. Yes. Okay, so dv dx is equal to minus w. So we had not utilized these things earlier that much. I had just mentioned in passing in class in the chapter on bending of beams, but this has a good application in this case. Why it is a good application, you will see in a moment. So now, effectively what we are having is that EI d4y dx4 is equal to minus w. This w is the distributed load. Now in this particular example, w is a constant. Okay, so w is a constant all along this x. So that's very good. So what we have is this situation that EI d4y dx is 4 is equal to minus w, and we just have to differentiate this, integrate this properly to obtain the solution for y. This is a good direct application of this updated theory because this equation is no longer represented in terms of the bending moment, rather it is represented in terms of the distributed loading. And because distributed loadings are so very common in beam examples, and please note that it need not be this kind of a constant value. It can be some kind of triangular load or some kind of arbitrarily distributed load also. It will work perfectly okay. Now, this is a fourth order linear differential equation. So you have to integrate this 4 times. And if you integrate this 4 times, how many constants of integration are you going to end up with?
4.
4.
Yeah, you're going to end up with 4 constants of integration. Which means how many conditions do you need in order to able to find out those unknown constants of integration?
4.
Naturally, 4 conditions you require to find out those 4 unknown constants of integration. Question is, what are those 4 constants of integration, or what are those 4 conditions? So I will tell you 2 of those conditions, the easier ones. So at x equal to 0, y equal to 0. At x equal to L, y equal to 0. Next, what can I write?
So
Sir,
at L by 2,
dx
dy by dx will be equal to 0.
0.
At L by 2, dy dx is going to be equal to 0. Now, that is a very clever application of your understanding of this problem, in the sense that this has a nice symmetry. But suppose instead of this kind of a uniformly distributed load, suppose you had a triangular load. Because this is a very initial example, I did not want to complicate it, but in a practical scenario, it is very natural for you to end up with a situation where the distributed load is not going to be uniform. It's not going to be a constant value. Then a priori you cannot predict where the maximum value of the deflection is going to be, in which case the trick that you are employing right now, that is not going to work out. So you need some kind of foolproof method of writing down the condition in terms of the overall given structure, instead of trying to cleverly exploit the symmetry of the situation, because in many situations the symmetry is just not going to be present. So tell me, from a more fundamental consideration, just by looking at the supports, if you can tell me what the other conditions will be. You know the answer, all of you know the answer.
So the moments are zero. Like.
Yes, very good. The moments are going to be 0. Okay, at both x equal to 0 as well as at x equal to L, you please understand that these are pinned supports. Okay, this is referred to as a simply supported beam, but as far as the reaction supports are concerned, this is a pinned support. This is a pinned support with wheels at the bottom, but this is a pinned support. So at the pins, you have already been studying from your first year mechanics that the moments are going to be 0, because the pinned supports are those kinds of supports which do not resist any kind of rotation. And because they do not resist any kind of rotation, they supply 0 moment. So at x equal to 0, your m is equal to 0, and at x equal to L, again your m is equal to 0. Now writing like this is fine, that m is equal to 0, but you understand that the equation that you are going to end up with from after integrating this 4 times is in terms of y. All right, so where is this m coming from? So look here, where is m? M is present here, okay? This is m. The expression for m is ei d square y dx square. You can utilize this thing, okay? So which means that ei d square y dx square at x equal to 0 is going to be 0, and this is implying that ei d square y dx square at x equal to L, that is going to be equal to 0. Okay, so you determine the expression of y in terms of the 4 unknown constants of integration. Then you differentiate that expression twice to find out this ei d square y dx square, and then you can say that that is itself the m, and then that expression you put equal to 0 and 0 at x equal to 0 and L, and you will be able to find out the constants of integration. So I want all of you to do this thing, and you will find out that after doing all of this thing, the solution to this entire thing, it will come out as y is equal to w by 24 ei times minus x to the power 4 plus twice L x cube minus L cube x. Please verify this, okay? Please verify this. So we'll continue with our discussions on Wednesday. We'll take up another example from the statically determinate case where there will be some kind of a change in the loading in between the beam, and then we are going to discuss statically indeterminate cases. All right. Thank you very much. Please go to your next class.
Excuse me, sir.
Yes.
Sir, I have it.
So actually, as we have known that dm by dx is equal to v and dv by dx is equal to minus 1, so we are utilizing this in this question, or is it really helpful in this question? Yes.
Which one?
For this problem, so we can solve it by 2 methods, no? By computing
Yes.
m as a function of x.
Yes.
So I'm thinking that the first one will be easy.
So yeah, so in this particular very simple case, the first one will definitely be easy, but I wanted to demonstrate the application of this second method. So through this easy example.
Okay.
Yeah, so definitely. So if you take up the first case, you just have to use 2 boundary conditions, that at x equal to 0 and at x equal to L, y equal to 0. Okay, it will be done.
So,
Yes.
so like we can find the center of application of this force and like find dy by dx and equate it to 0.
See, for those kinds of things, there is always going to be the danger that you are going to end up with a wrong condition. Okay. Plus, please remember that these kinds of problems as they become more involved, we don't do this by hand anymore. Okay, we don't do this by hand anymore. Rather, some professional engineers, what they do is that there are catalogs or there are handbooks where various kinds of fundamental solutions to these easier distributed loadings or easier concentrated forces are there. And in a real situation, they consider the superimposition of those various kinds of loadings to actually build up their solutions from those listed solutions. So that is referred to as the method of superposition. Another method, very modern method, is to actually code it up symbolically. The kind of things which I have introduced already in my previous tutorial sheets. Okay, now when you code it up, it is much more easier to instruct the computer to utilize the condition that the moment is equal to 0, or the shear force is equal to 0, or the deflection is equal to 0, just by telling it that, look, here you have a fixed end, or here you have a simply supported end. It's much easier to do that, because when you are instructing the computer or coding up it symbolically, you yourself are not that much bothered with how much laborious algebra you have to perform. Okay, rather your intention then is to just set up the problem in a very systematic fashion without taking into consideration the very special symmetrical cases or whatever little tricks which you can employ as a human solver of the problem. Because you are outsourcing this thing to the computer, your intention will be to systematically make the computer understand in a very general way that no matter what the situation, you can always use this and the solution will come. Okay, which is why I insist that please try to solve these problems in a very using these general kinds of boundary conditions. Okay, it is possible that you can solve a particular case or maybe 2 or 3 cases through some special considerations or tricks, but my advice as your instructor is that avoid that. Okay, it may be very intellectually pleasing for you to do that, but ultimately, from a professional experience, it is not going to help you. Okay, rather this is what I'm teaching you here, like identify the nature of the supports and write down the conditions associated with those supports from a very fundamental perspective that is going to always be reliable and foolproof. All right, everyone, please go to your next class.
Thank you, sir.
Thank you, sir.
Thank you.